Hello. If you should hear me by now. Let's see. You see the desktop? Can you can you hear me? Can you see the desktop?
Yes, Professor.
Okay. Okay. Let's see. Actually, there's nothing new to put up there today. We're going to pick up where we left off. We were going through the code in the render, and let me download the pictures too. We'll pick up where we left off going through the render code. Okay, now let's see. Actually, first, is there any question about the homework assignment? It's due today.
So for in the description,
I can't hear you.
can you hear me now?
Yeah.
Okay. So in the description, it says you just want the Java file for version 1, version 2, and the GIF.
Yes. Yeah. Yeah. Don't send me your frames. No sense wasting internet bandwidth on something like that.
Do you want the source code for our W and the
Oh yeah, did I forget to say that?
Yeah, it doesn't say.
Oh, darn it. I'm sorry. Yeah, I'm sorry. That's important. Yeah, you're supposed to send your N and your W. Oh, I wish somebody brought that. Yeah, because that's what you wrote. Yeah, right. So so you should send me 4 files. 5 files. This one, the animation, and your N and W. I got to remember to update that right after class. Yeah, that's a real good point. You should, the stuff you write is pretty much what I want you to be turning in. Yeah, if you wrote it, you should turn it in. If I wrote it, you don't have to submit it back to me. So the turn in will be 5 files then.
Okay. And the animation is for version 2?
Pardon me?
The animation is for version 2?
Yes. Yeah. You'll probably want an animation for version 1 just for your own while you're make sure everything's working. But yeah, the animation is of the version 2. Yeah. So after you've got version 2, then the animation you create a version 2 you send to me. Okay. That's a good point. So yeah, send your 2 models that you built. Yeah, I built the P, so you don't need to send that, but you should send the N and the W. Okay.
Should we resubmit if we already?
Okay. Please do. Yeah, I have Brightface set up so you can submit as many times as you want. Yeah. And if you see a mistake like that in the future, it makes sense that I want you to turn in the stuff that you write. So if I should forget to mention something, please, that way I can fix it up here as quickly as possible. Okay, so that's a good point. All right, anybody else got a question about the homework? Anything not working? Anything that isn't anything strange? Okay. Okay, so like usual, if you do have questions about the homework, send me email or arrange a Zoom meeting or whatever. Okay. So then let's go ahead and let's see, was there anything else? Before we start talking about the GUI stuff, let's go ahead and finish just stepping our way through all the code of the render itself. So we were using this triangle code as the thing to step us through the render. Okay, so we're now in that line of code there. That enters that's what enters the render for us. So we enter the render at the render method in the pipeline package. So open the pipeline package. There's the pipeline file. Okay, there's the renderer method. Remember, we're rendering a scene into a viewport. Okay, and we're not going to make any changes to the scene. We'll make a copy of the scene so that we can make changes to the models. We'll make copies of these, and we're mutating the viewport. So we're updating the contents of the viewport, but we're not going to, and we do need to modify the scene, but we don't modify the scene that's passed to us, because that's actually belongs to the program that's over here. This program really wouldn't like it if this scene got changed by calling the renderer, because remember, the next thing you want to do is create an animation. So you want to update that scene, but if the scene's been updated by the renderer, that's really bad. So that's why we have to be real careful about how we manage memory. We don't want this method to modify the scene. We do want it to modify the viewport. Notice that there's an asymmetry there. We don't want this modified. This program here thinks that its scene is its scene. It owns the scene, so it decides where things are in the scene and all that. And it wants the viewport updated. Now that's why this style of programming actually has problems. Yeah, and I mentioned every once in a while this idea of functional programming. You can kind of see what's going on here. Unless you have real good knowledge of what's going on, how would you know that this cannot be mutated? And this is the whole point, is to mutate this. This guy really should be the return value, because that's essentially his job, is to return a new viewport. But that doesn't work very well in Java either. So we just write a method, takes two parameters. One is not to be touched. This one's read only, and this one is to be updated. Okay. So over here, then we go through the steps of the rendering, and there's only two steps to rendering: the projection, then the rasterization. Okay, so it's a real simple render. There's only two steps to it. If we look at the pictures we have, remember, projection takes all these points and sends them into this plane. So then we have a smashed model. Okay, that's the projection step. It'll take the vertices, send them to the view plane, and give us a smashed model. Then the rasterizer will take the vertices and figure out what's in between them. What pixels should be painted in between the vertices. So the rasterizer is then going to create the picture in the frame buffer. So if you think about it this way, he's got different terminology here, but that's the model in camera space. You project the vertices to the image plane, and then you take the vertices in image plane and figure out what pixels in the frame buffer need to be turned on. So you end up with pixels turned on in the frame buffer. So camera space, image plane, and frame buffer. Okay, and right now after step one, we've got everything in the image plane, and now we have to start doing the rasterizing. And we started talking about the rasterizing. The rasterizer is in its own file. There's the rasterizer. In terms of this picture here, remember, this is this rectangle over here. That's or you can think this plane, this XY plane, is that image plane. The projection step put everything in here. We want to paint over here, which is the frame buffer. So we've got a picture over here. We want to turn it into pixels over here. But that's actually kind of hard to do. So we created this intermediate step. Remember, this thing here is called the pixel plane. This is the image plane, the frame buffer. This thing is called the pixel plane. Each one of these dots represents the center of one of these pixels. Okay, and we mentioned it. You can think of this image rectangle as being stretched over this pixel plane, and then like if you have a line segment over here, you'll get a line segment over here. And then what we're gonna do is, when we have a line segment over here, the line segment's probably not gonna pass through many of these actual pixels, but we'll decide which pixels are closest to the line, and those are the pixels we'll turn on over here. If you just went from here to here, if you just took the line in here and drew it in here, first of all, you can't draw in this thing because it's not a coordinate plane. It's just a bunch of little it's an array. And even if you did draw here, we saw pictures. It's not easy to figure out which pixels to turn on. When you work, remember, if that was working in, if you think of it, it's working over here. It's hard to work in this pixel plane where everything's just a box. Remember, we did, like, suppose you want to connect that vertex to that vertex. Suppose that's the endpoint. Well, let's see. So those are the endpoints of your line. It's not real obvious how you should go over and up. And like if you just go over, up, you won't get there. Should you go 2 over, then up 1, then 2 over, or 2 or 3 over? It's not at all clear. So for example, if I do this one, I certainly can't go over 2 over, up, 2 over, up, 2 over. That doesn't get me far enough. So I need maybe, how many? Maybe 3 over. That's probably not going to get me far enough. 4 over. Or maybe I should start by going, for example, maybe I should start by going up 1, then over a bunch. Then up 1, or should I do this? Up 1, over a bunch, up 1. Should I do this? Let's see, if I go over here, they don't meet. So at some point I need to switch to, say, okay, where should I switch? I have now 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, and 3 in the middle. Okay, should I do that? See, what do I have now? 1, 2, 3, 4, 1, 2, 3, 4, 5, 1, 2, 3, 4. And I'm not going to get them even. So what's the right one? It's actually really hard to figure this stuff out. Working in this world of little boxes is not easy. That's why we remember there's that paper that a pixel's not a little square. You don't really want to work with these little squares. It's not clear what's the right thing to do. That's not to go from here to here. That's probably okay, but so is this one that goes like this. That one sure seems okay too. 5 on this end, 5 on this end, 3 in the middle. I mean, you could even, like probably you would think that that's too extreme, this one. That's probably going to give you a pretty, not very good looking line. At the same time, it would be extreme to do this. That would probably be considered too extreme too, too short, or even more extreme. Too short on this end and too short on this end, too long in the middle. So you want something kind of balanced. So, but there was no obvious one for balance. Okay, 4 here, 4 here, 1, 2, 3, 4, 5 here. 4, 4, 5. Probably that's the most balanced, but you could also do 5, 5, 3. All right. When you get rid of little boxes and you switch to these little points, you have a more algorithmic, it turns out you can end up with a more algorithmic way of deciding which pixels to turn on. Okay. All right. So that's what our strategy is to not work in this world of little boxes, not go from here to here. We could, and a lot of graphics books teach you algorithms to go from here to here, but those algorithms turn out not to work. They're not used anymore. They were used in old graphic systems. They were used in old graphic systems when things were mostly black and white. So a lot of the textbooks give algorithms to draw lines from here directly into here. And it's still in all the textbooks, most of them, but it's a lousy algorithm because it only worked in the world of black and white. In the world of color and shading, you really have to go from here to here to here. And I'm not sure why the textbooks are still showing the ancient algorithm instead of showing a more modern algorithm, but and none of the graphics cards will use the old algorithm. And actually, this page here is about the old algorithm. This is the old algorithm. They all talk about this old algorithm. And that old algorithm works. It draws the lines in these boxes, but it doesn't work with colors. It doesn't work with shading. And it's, for some bizarre reason, everybody still describes this algorithm from this, I think it's from the 1960s, the very first graphic systems. And it's an interesting little algorithm. It draws lines in these boxes directly. It does not use this pixel plane idea. It does not use the pixels are a point idea. It uses the pixels are a box idea, which is everyone agrees is wrong now. Okay, so you see massive amounts of this stuff here. Okay, but people don't use it anymore. Okay, it works, but it only works in black and white. Okay? But this page is real nice because this page gives you a good sense of what the problem is. The idea is, and you can play with this little thing here. You can just like if I want to go from there to there, it's easy. Notice 45-degree lines are, well, see, did I do what 45-degree? Yeah, I almost did 45-degree. Okay, so 45-degree lines are real easy. Horizontal lines are easy. Things get tough when your slopes are not nice slopes. When things aren't a nice slope, then things get kind of hard. Okay, so now what is going to be our algorithm? Okay, so our algorithm is to take a vertex here and a vertex here, not to go here and here and try to figure out what boxes to fill in. We're going to take the vertex here and the vertex here and map them to over here and get two vertices here, but the vertices won't land on pixels. They'll probably just land somewhere in the space in between pixels. Okay, and so we'll end up with a picture that looks something like this. You'll have a line over here, and then when you send its vertex 0 to here, it'll end up being somewhere not quite on a pixel. And then when you send its other vertex, it'll end up over here, not quite on a pixel. And here's another line. When a vertex from over here gets sent over here, it just ends up somewhere in this plane. Okay, very unlikely to land on a pixel. Okay, then the next step we'll do is we'll snap the vertex to the pixel. We will shove this over to here on the left endpoint and the right endpoint. So this left endpoint will snap to here. This right endpoint will snap to here. This one will snap to here. So we snap it to what we call snap to the grid. We snap it to the grid of pixels. That's not a good thing to do because you can see in this picture it makes the blue line and the black line flip over, which is not correct, but it makes the code a lot easier. Real graphic systems won't do this. So a super sophisticated graphics card like your render, the GPU won't do this. They won't snap these to the grid. At least they don't. No, they don't. They don't anymore. They used to, but they don't anymore. But it's really hard to write the code that doesn't do that. If you don't snap this to the grid, it's actually pretty hard to write the code. I tried it once and I gave up after a couple days. I couldn't. I can show you what kind of goes wrong. Suppose I didn't snap this one to the grid. Okay, I need to start rasterizing somewhere. Should I start? So I probably would start rasterizing on this pixel here. Okay, so that's not so bad. Now, but look at this one. Suppose I don't snap them to here. Where should I start rasterizing? Should I start on this column or should I start on this column? If I start on this column, I have to back up this line over to here. Okay, that doesn't seem so bad. But now think about, suppose this pixel was down here. Suppose this vertex was down here. Okay, suppose that pixel was right over where the mouse is. Now I got a real problem. Do I start in the left-hand column or the second from the left column? If I start in the left-hand column, I'm supposed to, like here, I would project down. But if I start here and I project down, I'm off the screen. And then I have to worry about what to do. On the other hand, if I project over to here, I'm projecting up, and then I'm dropping part of my line. And you end up with, if you try to render starting right there, you end up with a huge number of special cases near the edges of the screen. Everything goes wrong near the edges of the screen. Should you back up or should you go that way? If you back up, you could end up backing up off the screen. If you go that way, you end up losing a pixel on the end, and then you get lines that are jittery when they're moving around a little bit. So if you don't snap these things to the grid, you end up with gazillions of special cases of what happens when you're near the edge of the screen. Okay, and trying to write them all, it just ended up being extremely ugly code that just had to do case after case after case of, like, what if you were down here? What if you were over here? What if? And that's actually what they do. Is the real rendering, the modern rendering pipelines take this little square and divide it up into subsquares called subpixels, and they snap to the subpixels. So they might take this pixel and divide it up into 16 subpixels and then snap to the subpixel. So they do snap to a grid, but the grid is a subgrid, and then they do some extra work. Okay, so they do subpixel grids, and they might do 16 or 32 subpixels in a pixel. Okay, so that's what they really do. They snap to the grid, but they snap to a subgrid, not the grid that's here, but there's an imaginary subgrid of 16 subpixels inside here. That's what your GPU would do. So eventually they're going to snap to a grid anyway. So to make our code much simpler to read, we'll do it kind of the old-fashioned way. We'll snap to this pixel grid, snap this one to this one, this one to this one. Notice if you're going to snap to a grid, you could have two lines flip over anyway, but there'll be two lines that are next to each other within the subgrid, so they're actually not going to flip over because they're going to still end up being on this pixel here. Okay, so if you use subpixels snapping to the grid, especially if you use, well, I think they use 16 subpixels, you don't see it. You won't see two lines flip over like they do here. Okay, you have to do more work, but then you end up solving the problem of lines like these flipping over. You know, you'll do more work, and you won't have a bunch of special cases because you're going to snap to a subpixel. You just have to do a little bit more numerical work. Okay, so we're going to keep things simple. Snap to the pixel grid. Okay, that does mean that sometimes two lines that are real close together again could possibly flip over, but that's okay for us. No one's paying us money for this renderer, so no one's going to complain. Okay, all right. So now, once you've snapped that to there and that to there, then you write the equation of the line that connects those two vertices. Okay, so after snapping this line to the grid, now that might change the slope of the line a little bit. I mean, there is a picture here. This was from another. Notice that that blue line, when you snap them to the grid, becomes a straight vertical line. So the slope, changes the slope. That one snaps to there. This one snaps to there, and the line becomes vertical. So you could be changing the slope a tiny amount. Okay. Here, when the line moves, notice that when the line is moved to the right a little bit, see that blue line, this is supposed to be what's wrong with snapping to the grid. The blue line is moving to the right. So notice that it's on the edge here. Here it's about the middle of the pixel. And here it's moved over to that edge of that pixel. So it's in the next frame, that end will be in this column, while this end's still in this column. So now the line straddles two columns. So now the line's no longer, the red line is no longer vertical. The red line is going to be drawn at a diagonal. So it'll be a few pixels over here, jump over, a few pixels over here. What that means is in an animation, this blue line was a vertical column of pixels, then a vertical column of pixels, then a jagged column of pixels, and in the next frame, it'll be back to vertical column of pixels. Because in the next frame, the blue line will be all in that column. And if you watch this line move in an animation, it would shimmer because it would be changing from vertical to slanted, then to vertical, slanted, and that causes visible artifacts. So this snap to grid and this would be like the edge of an object. So this blue line might be some edge of some object that's moving to the right, and the edge is jittery. The edge is vertical, vertical. See, the red line is what gets rendered. This snaps to there, this snaps to there, so you draw the red line. Then the next instant in the animation, that snaps to there, that snaps to there. That blue line is parallel to that blue line is parallel to that blue line. The blue line is moving to the right, but notice how its rendered line is vertical, vertical, not vertical, 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 not vertical. Okay, so you get weird effects in animations if you do this snapping to the grid. Okay, so now, after we snap to the grid, we find the slope of the new line. Okay, so after snapping to the grid, because the slope of the new line might be different than the original slope. You know, snapping to the grid can change the slope a tiny bit. Okay, now in the code, we get the two vertices of the line. Okay, you know, here's the line segment. It's got an index into the vertex list. Get the vertex with that index, call it V0. Get the vertex with that index, call it V1. So there's the two endpoints of the line. That's the two endpoints as they really are. That's the two endpoints as they really are. Okay. Now, then transform them. That's not these two vertices yet. That would be the vertices in here. So grab the two vertices in the image plane, send them to the pixel plane. Sending them to the pixel plane are these, there's sending one pixel to the pixel plane, and there's sending one vertex to the pixel plane. This is sending V0 to the pixel plane, and this is sending V1 to the pixel plane. Okay, so you send them to the pixel plane. Okay, then snap them to the grid, round them. Okay, so round them. So, okay, so start with a vertex over here, send it down here, then snap it to the grid. Okay, and get the vertex out of the model, send the vertex to the pixel plane, snap it to the grid. Okay, now we want to compute its slope because we want the equation of the line. But remember, we have to worry about, remember another picture. We need to worry about lines are slope less than 1 or slope greater than 1. If lines are slope less than 1, we rasterize them by walking this way and going 1 pixel over, 1 pixel over, and decide what pixel to draw. So we can move to the right. Now this is drawn, this picture is drawn in the pixel plane, or in the frame buffer. We're really going to do this in the pixel plane. I should draw a line like this in this picture. This line is actually drawn in the frame buffer. It really, I should have drawn it in here. Okay, so but the idea is that if the line has slope less than 1, you want to walk this way. If the line has slope greater than 1 and you walk this way, you end up going over and up, over, up too much, over, up too much, and you get gaps in the line. So you have to walk the line that way. You have to walk the line in the Y direction, and you would go up and over, up and over, up and over, up and over. You go up and over. Here you go over and up, over and up. And it doesn't matter if the slope is positive or negative. If the slope is negative, you go over and down, over and down, over and down. The key is whether it's really whether the absolute value of the slope is less than 1. Okay, so this picture is good for a slope that's between 0 and 45 degrees and between 0 and negative 45 degrees. So this is good for positive and negative slopes. Same with this one. That's a positive slope. Then there's a negative slope that goes like this. Okay, there's a negative slope that would be in this over here. That would still be like this one. We're really interested in the absolute value of the slope, whether the absolute value of the slope is greater than 1 or the absolute value of the slope is less than 1. Okay, so here's an if statement. Okay. Oh, actually, I'm sorry. First, we check that what if the two endpoints of the line are on top of each other? what if the line actually is just a pixel? It turns out it's worth treating that as a special case. If the two endpoints of the line lie on top of each other, so if the left endpoint and the right endpoint of the line are just on top of each other, you shouldn't rasterize the whole line. Okay, so if the left endpoint and the right endpoint are on top of each other, now that could be that you start, let's see, that could be that you started with a line that looked like the following. Whoops, not that one. What if you had a line where this vertex was here and the other vertex was there? Just what if the line just stretched across one pixel? Then when you snapped it to the grid, both ends would snap to there. So this could be a very short line that starts in one pixel and ends in the same pixel, and it snaps to the same point. Okay, so, or it could be a line that was actually just starting and ending at the same point. A line that starts and ends on the same point is a tricky way to draw a point. If you want to plot a point, a lot of graphic systems don't actually have, like Java library does this. There is no way to plot a point in Java's graphics library. You have to draw a line that start and end at the same place. Instead of having a point, draw a point, for some reason they chose not to have draw a point. If you want to draw a point, you draw a line and you give it two vertices for the endpoints of the line that are on the same place. Okay, all right. So we want to, if the starting point and the ending point of the line snap to the same pixel, we want to treat that as a special case. So that's what this does. Okay, all right. And it's worth looking at what we do here. Okay, remember we're moving from here to here to here. Okay, so now we've got a line that's very short up here. So it maps down here to a tiny little line segment where both ends snap to this pixel here, say. So both ends are on that pixel there. Okay, so what we need to do then is compute what pixel over here, what this logical pixel maps to some physical pixel over here. So we have to compute the physical pixel. So once we know what pixel we want to draw in logical pixel, we have to figure out what pixel it is over here. Okay, the only big difference here is that the origin is in the lower, over here, the origin's at the center. Over here, the origin's at the lower left-hand corner. Over here, the origin is the upper left-hand corner. So there's a change in coordinates, like from here to here, this is W wide, H high, and this is W wide, H high, but they don't have their origin in the same place. This one, 0, 0 is this guy here. This pixel there is 0, 0. That box up there is 0, 0. See, this box, I can't really highlight. Can I highlight? Yeah, whatever. That box is box 0, 0. That pixel there is pixel 0, 0. Okay, so the x coordinate from here is the same as the x coordinate here. I'm in the same column, but I'm in a different row. This pixel down here, which is in the 0 row, so to speak, y equals 0, is actually in the h minus 1 row down here. Okay, because 0 is up here. This is row 0. This is row 0 pixels. This is row h minus 1, height minus 1 down here. Okay, so down here, here's where I take the x and y logical pixel coordinate and turn them into viewport coordinates. So there's the x, y viewport coordinate. Okay, the x coordinate is just shifted over by 1. You have to round it to an int and shift it over by 1. The y coordinate is rounded to an int and then subtracted from the height. Okay, so shifting viewport coordinates to logical coordinates, changing logical pixel coordinates to viewport coordinates. Okay, so if you've got just one point to plot, all you have to do is change it to viewport coordinates, but then do the clipping step. So we haven't talked about clipping. What if your line, what if your vertex is from out here somewhere? Then it maps to somewhere out here. Yeah, it's outside of this here. That'll be outside of that viewport. Okay? So remember, if your vertex is outside of that little rectangle, it'll end up with a coordinate that's really outside of that box. So we'll end up with a coordinate that's really outside of this box. Okay. If we want to clip it, anything that's outside of this box shouldn't be drawn. So we go down here. If our coordinates are, if our viewport coordinate is not, well, we want to plot it if the viewport coordinate is greater than 0, less than the width, greater than 0 in the y direction, and less than the height. So this is the condition for we should draw it. Okay, so that's the condition for yes, we should draw the point. It's inside the viewport. So if it's inside the viewport, we set the pixel in the viewport. If it's not, if this is false, we log a clipping message. Okay. Okay, we log a clipping message just to let people know. So see, if clipping and debug, see, there's the debug thing. So if clipping is turned on and debug, then we log it. Now, if clipping is turned off, we put it in, we set the pixel. Now that's what causes the folding over. Remember, if something's off the screen and you don't clip it, it folds over. Anything that goes off the right edge of the screen reappears on the left edge of the screen. Okay, that's because of the column, the row major form of our frame buffer is stored in row major form. Remember, if you think about this guy in the frame buffer, this guy is not a two-dimensional array. It's a one-dimensional array that just keeps on going. This second row really appears right after the first row. And then the third row is really, again, really part of the first row. It's just a really long row. Remember, that's what we mean by row major form. That this frame buffer in memory really is one long one-dimensional array. Okay. Now, what happens when you go off this edge over to here? What happens when you get to over here? Okay, think about it. This thing is really a one-dimensional array. So if you're in this row and you go past it, you're really just down here in this pixel. If you go over one pixel here, you're really that pixel there, because that row follows this row in memory. If you're 3 pixels over here, you're in the third pixel down here. You notice you're actually not, if you go off the right edge of this screen, you don't actually come back in the left edge of the screen. You come back in the left edge one row down. And if you actually look real carefully at those images, you'll see that when something goes off the right edge of the screen, it actually comes back on the left edge one row down, because this row of pixels follows that row of pixels in memory. So if you're actually over here, you're actually down here. Okay, so if clipping is not turned on, okay, you'll plot the pixel anyway, and then the frame buffer will just plot the pixel where it belongs in the one-dimensional array. When these coordinates are over here, I'm sorry, when the coordinates are over here, you're really just another row down in here. And if you go really far out this way, you're just going more and more rows down. Eventually, if you go too far to the right, you'll end up going off the bottom, and then you're actually off the array, and then you get an error message. If you go off the bottom of this array, then the frame buffer complains. If you go off the right edge a little bit, you're just in the row below. If you go off the right edge a real lot, you'll go from row to row to row to row to row, and then eventually you'll fall off the end of the array, and then the frame buffer complains when you've finally gone off the end of the row major array. Okay, right. So that's this special case here of a single pixel. Where the line is a single pixel. Okay, so now if the line is not a single pixel, now we need to check its slope. Okay, so here is the test of slope. Okay, now slope is change in y over change in x. Okay, if the numerator is less than the denominator, the slope is less than 1. I hear a question for you. Why am I doing it? this way? Why don't I just compute the slope? Why don't I just check if the slope is less than 1?
You want the absolute value of the slope?
Right, okay, but why don't I just take the absolute value of y1 minus y0 divided by x1 minus x0? Why do I do it this way instead of, divide by, why not do numerator divided by denominator and forget about this part over here?
Division by 0 could happen, maybe?
Yeah, exactly. Well, as soon as I start dividing, I got a bunch of things to worry about. I could, first of all, division's a complicated operation. It slows me down a little bit. If I want to know if a ratio is greater than 0 or positive or negative, greater than 1 or less than 1, I could do the division, but I have to, first of all, the division's slow. I have to worry about a vertical line. See, a vertical line has change in y being 0. So then I have to worry about dividing by 0, okay? So if I do this trick, I don't have to worry about dividing by 0. I mean, I know this is the numerator, this is the denominator, okay? But I don't have to worry about this. If this is 0, I'm just still worried about whether this is smaller, less, if 0 means infinite slope. If the denominator is 0, the line is going up and down. That just means it has a very large slope. That's all I care about. I want to know, is the line more vertical-like or is the line more horizontal-like? I'm trying to figure out which lines. There's this 45-degree line. This is dividing between more vertical-like and more horizontal-like. A vertical line has slope infinity because you're dividing by 0, but that's still that's vertical-like. That's all I really want to know. So I don't compute the slope. I just compare the change in y, the numerator, with the change in x, the denominator. If this is less than 1, I've got a horizontal-like line. The slope is less than 1. Okay. See, the comment says I'm really checking if the absolute value of the slope is less than 1. Okay. So the comment's telling me what I'm thinking. I'm thinking, is the absolute value of the slope less than 1? But I don't want to compute the slope because the computing the slope makes me divide, which means I might divide by 0, and I got all kinds of things to worry about. So I cheat and I compare the numerator to the denominator. Okay, so little tricks like that can make coding a lot easier. If I was actually computing the slope, I'd have to have a special case for what if the slope is infinite? What if I'm dividing by 0? Okay, and I don't want to do that. So this works much better. So this case is the more horizontal-like lines. And then down here, the else case is going to be the more vertical-like lines. Okay, and now here I'm writing code in kind of a sloppy way. This is a more horizontal-like line. Okay, and this is the more vertical-like line. And if you look, you can rightfully complain that that code almost looks exactly the same. You can say, you're duplicating code. You're never supposed to duplicate code. And the answer is yes, I'm duplicating code. And I could try to abstract this, but I decided it ended up being too hard to read. I mean, I want this to be easy for you to read. So I actually just left it as two cases, a horizontal line-like case and a more vertical line-like case. The code is definitely very redundant, but it just wasn't, I mean, to abstract it out would have left it being a little bit, I think, a little bit harder to read. Okay, so I left it redundant. Okay, so this block of code is a little bit easier to read now, but it looks a heck of a lot like that block of code. Okay, just so essentially just some x's and y's have been swapped. Okay, and actually later on in the render, when we're more used to this, in a later render, I did abstract this. It doesn't have two blocks of code like this, but it becomes a little bit harder to read. Okay, so let's look at what you're going to do here. So this is the case that's more horizontal-like. So what we're going to do is take a line that goes from a pixel here to a pixel here, and we know the equation of the line, and the line is got slope less than 1, so it's horizontal-like. And essentially what we want to do is walk from pixel to pixel to pixel to pixel. And just imagine it's one of these lines. Here's what you're going to do. You're going to walk from pixel to pixel to pixel, and you go here, and the line is always between two vertical pixels. Notice how you're between there and there. You're between there and there. And you're between there and there. You're always, the line is between two pixels. All we're going to do is take that x coordinate, plug it into the line to get the y coordinate, and round it to a pixel. Then take that x coordinate, plug it into the line, round it to a y coordinate. So we're just going to plug the x coordinate. Now the x coordinate is going to go from here to here to here to here. We'll take an x coordinate, which is increasing by 1 each time. You go from that pixel to that pixel to that pixel. We will walk along the x coordinates, pixel by pixel, plug into the equation of the line, get the y value, round it. Okay? And then then the xy coordinate is the coordinate to plot. Okay? So this for loop walks the x coordinate in ones, okay, until you get, and you start at the left end till you get to the right end. You walk the x's by 1, and then here's a cute little trick. What do you do with the y's? Every time you go over, if you take a point on a line, every time you go over 1, so notice I go over 1 unit, I go up m units, because the slope is m, which is m is the slope, but that's rise over run, but the run is 1. So I've got a run of 1, so the rise is m. Run of 1, rise is m. So I can do that here in the for loop. If I have a run of 1, the rise is m. Okay, so the for loop is marching me from that point to that point to that point to that point. Okay, so so it's going over 1, up, rise, over 1, up, rise. Okay, so the for loop's actually marching me down the line. So this for loop is actually giving me the coordinates of the pixel I want. So here I convert it to viewport pixels. So here it's converted to viewport coordinates. Notice that this is actually doing the equation of the line for me. Now, I don't even really need to ever plug in to the equation of a line, because if I always go over 1, up m, I'm staying on the line. Over 1, up m, I'm always staying on the line. So the for loop's just moving me from point to point to point on the line, but then I want to round to the pixel. So here's the rounding right there. Okay, so y is on the line, that rounds it to being on a pixel. Okay, so the for loop is computing the point on the line, then I round it to a point that's actually a pixel point. So the y coordinates on the line, round it to a pixel. Okay, y coordinate is on the line because I went over 1, up m, but then I round it to a pixel, and then I convert it to viewpoint coordinates. So I subtract the y coordinate from h to get the, because remember, up here, you have this weirdness that this is the zeros in the lower left-hand corner in this coordinate system, zeros in the upper left-hand coordinate in this coordinate system. So the x coordinates here and here are the same, but the y coordinates are flipped by h. You know, when you're up on this row, you're in row 0, but up on this row is row y. When you're down here, you're in row 0, here in your row y minus 1, or h minus 1. Okay, all right, so down here, if I'm walking a 45-degree, a slope that's less than 1, so I'm in the case of slope less than 1. Okay. Oh, then there's another trick here to have to worry about. So I kind of skipped from here to here, and I forgot to show you what this little thing does here. There's another thing you have to worry about. I'm always pretending that this is V0 and this is V1, so that I'm walking from left to right. But there's no reason why that's V0 and that's V1. It could be that that's V0 and that's V1, so the line moves from right to left. But then I have to have like one for loop to worry about this direction and one for loop to worry about that direction, because the for loop going in this direction is incrementing x's. If I'm going in this direction, I'm decrementing x's. So what I'm going to do is I'm just going to check. The first thing I check is am I moving from left to right or right to left? I want to move from left to right. If I'm moving from right to left, I just flip the endpoints. I do a swap. Okay, so we want to rasterize from left to right. If by any chance we're actually rasterizing from right to left, so V0's over here and V1's over here, we just swap the two endpoints. There's a swap. Okay, these lines of code do a swap of the two endpoints. Okay, so we end up always walking from left to right, and that just makes things a little bit easier. Otherwise, I have to do funny things with this for loop. This for loop has to have a variable here that could be +1 or -1. So sometimes it's walking to the left and sometimes it's walking to the right. But that makes this for loop harder to understand and more likely to be buggy. So it's easier just to say swap them. Okay. So this is just notice this is a step you have to check. If you were trying to optimize this code to make it as absolutely fast as possible, like in a real render, like in a graphics card, you probably wouldn't want to do that test. You'd probably want to somehow very carefully write this for loop, very, very carefully, so that it sometimes walked from left to right and sometimes walked from right to left. But you wouldn't want to have to do this test. And if you were making a lot of money off this and had time to really write your code carefully and debug it carefully, you would probably not do this and write this for loop real carefully so that it did something tricky, so that sometimes it was walking from left to right and sometimes walking from right to left. Okay. In our case, I'm trying to make the code simpler to read. Okay, so I think this is simpler to read. Just the idea is you want to walk from left to right. So if the endpoint, if the start is on the right and the end is on the left, swap them. Okay, so that's what this does. This swaps them. Then this for loop can always walk to the right. Okay, all right. So notice that there's lots of little cases to check. Okay, now down here is where the clipping happens. Once I have my viewport coordinates, just like with a single point, I check if the pixel is actually in the viewport. If the pixel is not actually in the viewport, if it's out here somewhere, I don't want to plot it. Or if I do plot it, it'll fold over down here. So I let you turn off or on the clipping can be turned off and on. If a point is out here and clipping is turned off, it'll show up inside over here. If the pixel's out here and clipping is turned on, it just gets dropped. It doesn't get drawn. Okay, so now there's an interesting problem here. Okay, this is actually not a good way to do clipping. I'll show you in a second. What this does is it takes a line segment and rasterizes it, and then for every pixel on the line, it decides whether to draw the pixel or not. So we're walking the whole line down here. See, we're walking the whole line, and we're deciding for every pixel on the line, should we draw the pixel or not, and where to draw it. Okay, let me draw a little picture. Here's a view rectangle. Okay, so it's got the x-axis going here. Let's see, where's
I think if you hold shift, you could draw a straight line.
does it have a trick for getting the lines evenly horizontal or whatever? Okay. See, okay. Now, what if I have a point that starts inside here and goes out like that? Okay. What I'm going to do is I'm going to rasterize this by starting here and walking this line and saying, paint that pixel, 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 don't paint that pixel, don't paint that pixel, don't paint, and I'll go all the way to the end, okay? What happens if this line is really far away? Okay, let me show you an example what I mean. Go to the directory that holds the code for the render. Okay, here's a file called something wrong. Okay, this line draws this code draws a single line between two vertices. There's two vertices and a line segment. Compile it, run it, and it's caught. You know, nothing happens. Okay, the thing's going to run for a very long time, maybe forever. What I did is I created this line segment so that in this picture, the end of this line segment is essentially out at infinity. So there's essentially almost an infinite number of pixels for this line to draw. And the code is actually stuck in what appears to be an infinite loop while it's trying to compute all the pixels on that line. Okay, so it's literally stuck now in this for loop here. Where is it? It's stuck in this for loop here, walking essentially an infinitely long line. Okay, and you can see it here. The line started at 0, 0 and went to 1, 1. Okay. Okay. Then it projected to 2, 2. Now see, look what it projected to, some huge number. It's actually not even that big a number. It's a few billion. Okay. But it projected to a very long 9, and it's trying to rasterize now the line from 2, 2 to 1, whatever that is, to 1 trillion to 1 trillion. I'm not sure what that number is, how many zeros there are in there. 1, 1, 2, 3, 1, 2, 3. So it's like 100 billion pixels. Okay, so it's still rasterizing. Okay, I'm not sure how long this is going to take. Okay, so this is not a good way to do clipping because you can accidentally get into infinite loops, because it's not hard to get a line segment that goes out very, very far, and then the rasterizer is trying to rasterize a ridiculously long line. We need to come up with a better way to do clipping. Okay, clipping in the rasterizer, it's something that can be done. Okay, I mean, we're doing it, but it has the disadvantage that you have to be very careful. You could accidentally rasterize what essentially is an infinitely long line, and then your rasterizer gets stuck rasterizing pixel after pixel after pixel after pixel. So we're going to come up in the next, in another renderer, we're going to do a better clipping algorithm. This clipping algorithm is used by some renderers, but it's got this disadvantage. This is clipping in the viewport. You're clipping in the viewport by essentially saying, if a pixel lands outside the viewport, throw it away. So that's clipping in the viewport. We'll actually want to go back over to here and clip over here. We'll actually want to clip right there. We're going to eventually say, well, wait a minute, if this thing sticks out here, let's just clip it right there and throw away all this stuff out here. We'll actually go back and clip here, not clip here. We'll clip here. We could clip here, we could clip here, we could clip here. We're going to go back and clip here later on. It's a little bit harder. It takes a little bit more code to clip here. It actually takes quite a bit more code to clip here than here. Clipping over here is real easy. It's just a little simple if statement. Okay? Clipping is real easy. It's just this if statement. Okay? If you're not inside the viewport, don't paint the pixel. If you're outside the viewport, don't paint the pixel. If you're inside the viewport, paint the pixel. But that requires you to loop through all these pixels. And you can hear it's still trying to walk that very long line. Okay? It eventually will finish walking that very long line, and then it'll be done, and it'll output the frame buffer. But right now it's stuck inside the render. It's stuck inside the render, trying to render all the pixels on that one very long line. Okay, so that's not a good that's not ultimately a good clipping strategy. It's the simplest clipping strategy. That's why some renderers use it. Some renderers actually do use this clip in the frame buffer, the viewport. Clip in the viewport's not that uncommon. It's got some advantages. Mainly, it's simple. Okay, but it's got the disadvantage that you can lead to it can lead to this kind of problem. So there are ways around this. There are ways of combining the two clipping algorithms, and some people, what they really do is they do a two-step clipping. They clip to a box slightly bigger than this over here, and then they clip to the actual edge of the viewport over here. So they clip to like a big region over here, but that leaves you with lines that potentially go a little bit outside of here, but not infinitely far out here. So they clip twice. They clip once over here and once in here. And we'll see why they would want to clip twice. Okay, so we're going to clip over here eventually, and that'll be our only clipping. But some graphics cards clip over here first, then clip over here second, and there are advantages to doing it that way also. Okay, all right. So now, if we go back to the code down here, that's the whole clipping. That's the whole rasterization algorithm. The only thing left is when the slope is larger than 1, you walk the line the opposite way. You walk the y direction going up, and every time you go up 1, you go over to the right by m. So this is walking in the vertical direction. Otherwise, the code is exactly the same. Every x and y are just swapped down here. You just essentially have the x's and y swapped. So this code looks almost exactly like this code, just the role of x and y has changed a little bit. But I went ahead and left it redundant like. Okay, I left it redundant like, just kind of makes it easier to read this code. Here you're walking in the y direction, which is walking up the frame buffer, and moving to the right or to the left by the slope. Okay? Then this is just the logging code. Okay. All right. At this point, we've stepped through the render method, renders one model at a time. If the model is visible, it projects all the vertices in the model into a new model. Remember, we said we're not going to mutate this guy, so we create new models. This model's the mutated version of that model. So I do not mutate that model, because that would mess up the person who created the model. I don't want to mess up his model. So when I do this mutation, I do it in a new model. Then I rasterize for every line segment in the mutated model, I rasterize the line segment into the viewport. Okay, so this rasterizes every line segment into the viewport, and then you're done. Okay, so that's the whole render. Okay, and notice that this thing's still trying to, you can see how you think that a computer would be fast enough to rasterize a line segment that's long, but that's actually a lot of pixels. That's a lot of pixels. Okay, so I'll just kill that. Okay, but so clipping in the viewport it's simple. Clipping in the viewport is simple and it's used, but it's got a real danger to it. You could be clipping a line that's essentially infinitely long. So you either have to solve that problem or do a different kind of clipping. And what we'll do is we'll switch to clipping over here. It's a little bit harder, but it turns out that it turns out to be way faster. Okay, a little bit harder to do. This requires a little bit more code, but it turns out to be way faster, and it solves this problem of lines that go off forever. Okay, all right. That's the whole rendering system. Okay, that's the rendering system. It's a lot. It's not a lot of code, but it's a lot of ideas. It's algorithms. We're stepping through clipping algorithm, projection algorithm, rasterization algorithm. So it's really it's really algorithms. Okay, and these algorithms are buried in your graphics card. And almost nobody would write these algorithms unless they want to learn them. Okay, so it's only when you want to learn them that you would write them. As opposed to like the algorithms you learn in the algorithms class, like searching and sorting algorithms and traversal of tree algorithms. You use those all the time. You do write tree traversal algorithms. You do write graph traversal algorithms. You do write searching and sorting algorithms. Even though they're built into libraries, you still really need to use those algorithms. These algorithms are kind of quirky in that you would never write a rasterization algorithm unless you were responsible for writing a graphics library. Like even if you write a game, people who write games never write rasterizers. They use the rasterizer that's built into the graphics card. But it turns out that when people who write games need to understand the graphics card really well, it turns out that if you don't really understand what's going on in a graphics card, it makes it much harder to understand how graphics cards work and how to optimize your games and why certain things are a good idea and certain things are a bad idea. So it turns out that really understanding the algorithms is a good idea. And the best way to really understand algorithms is to read the code. Okay. So I think this is a really good way for, even though you can make the case that this is dumb because no one's ever going to write a rasterizer, except for unless you work for NVIDIA. And even then, they probably wrote their rasterizer 10 years ago and probably haven't changed it in 10 years. Okay. It's still, knowing how a rasterizer really works is going to eventually be really useful to understanding how graphics cards really work. So if you need to really know how to write graphics code, and good graphics code that uses the graphics card properly, it helps to really understand what the issues are. What is the graphics card dealing with? Okay. And this is the best way to understand what the graphics card is dealing with. And it's not that much code. It's this rasterizer. First of all, remember there's a lot of redundant code. So if you understand this part, you don't even need to worry about this part. So you're really only reading. The rasterizer is all of, as complicated as this rasterizer is, it's less than 100 lines of code. Okay, the rasterizer is less than 100 lines of code. Okay, it's not the simplest code, but it's not a lot of code. It's still less than 100 lines. When we rasterize triangles, it won't be that much more code. Rasterizing triangles is a little bit harder than rasterizing lines, but it'll actually be only a few lines of code longer than what this is. So a lot of the ideas of rasterizing a triangle are still here already in rasterizing a line. Okay. Okay. Let's see. That's pretty much it for the rasterizer. I'm trying to remember if there was anything in the rasterizer that we haven't talked about. Anything in the renderer that we haven't talked about. No? Okay. Okay. Let me show you, we got a couple minutes left. Let me just show what we're going to be doing next. I'm going to use Dr. Java for something. I'm going to show you like something real quick in GUI programming. Dr. Java's got this interactions pane over here. Okay. Let me show you how simple GUI programming is. I want to create a graphics window. In Java GUI land, a JFrame is a window. Okay, I just created a window. Where is it? Well, you don't know what it's. I created a window object. I just told it to show itself. There it is. Okay, there's my window object. Okay, JFrame dot. Notice I created a GUI. I have a you know, 2 lines created a GUI. I haven't done anything with it, but it's there. Okay. If I want to hide it, remember I said that libraries have this idea of a variable that can let you make things appear and disappear. Notice that that window's still there. Notice that there's a set visible. I can make it come and go. Okay. I think this is the right code. I can change its size. Oh, notice that this hello was what's in the title bar up here. So the string I gave to the constructor for the JFrame put the string in the title bar. See, I just set its size. Okay, I can now see. This is kind of fun because most people don't think of it this way, but the GUI library is just like any other part of Java. You can just, if you're in this interaction pane, you can just create GUI objects and make them move around and do things. You can move this window around. You can set where it is on the desktop. I can change its size, and I can add something to it. Let me add a button to it. Okay, so I need to import. Oh, I already imported all the swing, so I don't need to import anymore. I imported everything from JavaX Swing. So I'm going to say jframe.add a new J button. Okay. Okay, I added a button to that guy. Now I have to tell the JFrame to show itself. See, there's the button now. Now that's weird. The button took up the whole window. That's not really what you expect a button to be. Okay, because I'm not doing this stuff very well yet. Okay, but notice that I created a window, I created a button, I put the button in the window. This is what kind of we're going to start talking about, this kind of GUI programming, where our objects are, these are just regular old Java objects. This is an object in the heap, but that object in the heap represents something that can be drawn in the window. This button is an anonymous object in the heap. I didn't give it a name, but I added it directly to the JFrame. So the JFrame is holding a reference to that button object. So it's not really an anonymous object in the heap, but it's an object in the heap, but it represents something you can draw on the screen. So we're going to start learning about these GUI objects that you can create and then display them or hide them. Like if I down here, I can just say set visible equals false, then it disappears. And then set visible equal true, make it come back again. Okay, so I can send message. I send that message to that object. See, I'm sending a message to that object, but that message has the effect of telling the Java system to change what this thing looks like over here. Okay, so that's the GUI system. You have these objects. It's object-oriented GUI programming. The objects in the heap represent graphical entities, and when you send messages to the objects, the Java virtual machine keeps things on the screen up to date. Okay? The Java virtual machine is responsible for making sure that the visible aspect of this thing is kept up to date as I'm sending messages to these objects. So that's what we're going to start playing with. Okay, and we'll do a lot of it with Dr. Java, with this, because Dr. Java has this nice interactions pane. So you can instead of writing code and then running it and getting a GUI, you can actually kind of experiment and see how each individual line of code actually affects the GUI. And it's kind of nice to do it this way. It makes it, I think, it doesn't make the GUI programming look so static. You can actually see that the GUI programming is doing things as the code is executed. Okay, so that's what. Now, I'm going to update the website a little bit more. Here's a reading assignment. I'll put a link with some sample code up there. and then something you can play around with. And then on Thursday, we'll start playing with the code. So I'll put a link up here with a zip file that'll have some examples that you can play with like this to show you that how you can like play around with GUI code to get started with. And then we want to tie events. The really thing we want is this button should do something. That's what we call event-driven programs, event handling. How do you make this button do something? Eventually, we would want things like if you click a button, maybe something appears or disappears on we'll tie these buttons to our renderer. We really want to tie our renderer to the GUI system and tie things like GUI buttons to our renderer. And that's event-driven programming. So then we can write, you can write a game in our renderer, because you would tie GUI elements to the renderer, and then the GUI elements could make things happen in the scene that's appearing in the render. Okay, so I'll go ahead and quit now because we went over time. So that's where we're going to start. On Thursday, we'll start playing around with GUI code like this. Okay. Anybody got any question? Any last minute question?
Yeah, one quick question. Can you hear me?
Yeah, barely.
Okay. So for a point, just 1 point in the vertex list, would we have 2 identical elements, and in the line segment just 1 from 0 to 1, or would we have 2, 0, 1, 1, 0?
I say it again. I don't get. Say it again.
Okay, for drawing just a point, we would have 2 identical vertex elements, and then in the line segment list, we would just have 1 or 2.
Okay. There's 2 ways. If you want to draw, suppose you want to draw a point, you could do it 2 ways. You could create 2 vertices, both of them which are equal, and then create a line segment where the 2 ends of the line segment are the 2 vertices. Or you could create 1 vertex. Suppose it has index 7. Then you create a line segment with 2 indices, both of them being 7. See, the line segment has to have 2 vertices, had 2 indices. So the line segment has to have 2 indices, but you can make the 2 indices in the line segment point to the same vertex. Or you could have the 2 vertices being equal to each other. So you could do it 2 ways.
Okay.
The line segment must contain 2 indices.
Right.
The line segment could have the 2 indices being the same, or you could have the line segment having 2 different indices, but the vertex list has 2 vertices which are equal to each other. Either way works. The way where the line segment has 2 indices where they're the same index pointing to 1 vertex is the better way to do it. But it doesn't matter which way. You could do it either way. Okay.
Thank you.
All right. Anybody else? Any quick question before we quit? If you have a question about the homework, let me know. Okay, I'm going to put up I'll put up a zip file here with some GUI code in it, so you can play around. And you can read in here about the introductory stuff to GUI, and I'll put some code in there you can play with. Okay. So on Thursday we'll start talking about graphical user interfaces. Okay. I'll go ahead and turn off the sharing. What happened here? Oh, I got. Okay. Okay. So see you on Thursday. Bye.